In the last video, I talked about using the least squares criterion to estimate the simple linear regression model. And that means minimizing the residual sum of squares to find the estimated intercept and estimated slope so that we can estimate the equation y hat equals b0 hat plus b1 hat x. The question now that we'll address in this video is how well does that estimated model fit the data? Or another way of putting it is how well does that estimated model represent the population relationship that we are wanting to investigate, the relationship between y and x. And so to motivate that, let's consider some examples. So on this screen I've got 4 different data sets represented in 4 scatter plots. If we start with the top left one and ask the question, how well does the model fit this data set? I think we would have to say it doesn't really represent it very well at all. So think about the model as being represented by the line. So we're asking how well does this line summarize the relationship between y and x? Well, it really doesn't appear to be much of a relationship between y and x in this scatter plot. So this line doesn't represent that relationship at all. There is no relationship. Moving to the top right scatter plot, now we can see that there is a positive relationship between y and x. As x increases, y tends to increase. And so now this line tracks that relationship reasonably well. But there's quite a lot of random error in the model because these points don't lie along the line. In some cases they're quite far away from the line. And so I think we could summarize how well this model fits this data set as it fits okay but not great. Coming down to the bottom left, now the points still have that positive linear relationship and the line tracks that relationship quite well, and the points are a lot closer to the line. And so I think we could summarize how well the model fits this data set as pretty well. And then finally at the bottom right, now the points lie exactly on the line, all of them. They're perfectly linearly correlated. They lie along a straight line, and so now this model does a perfect job of fitting the data. So keep these 4 plots in mind as we work through 3 different numerical ways of summarizing how well the model fits the data. So those 3 methods are as follows. The first one asks the question, how close are the actual observed y values, so the points in the scatter plot, how close are they to the model-based fitted values y hat? And remember, the model-based fitted values y hat lie along the line. So thinking back to, let's work on these 2 examples. So this question is asking, so how far is this point from its fitted value along the line? And how far is this point from the fitted value on the line? And how far is this point from the fitted value along the line? So it's asking that questions about all the points. So is there a way that we can summarize the vertical distance of each point from its fitted value along the line? And the way that we do that is to calculate something called the regression standard error, which is given by the letter S. The second method that we're going to talk about in the next video, we'll talk about the regression standard error S in this video, and then in the next 2 videos we'll talk about the other 2 methods. But just briefly, the second method instead asks about the variability in y. and how much of that can we explain with our model. And that will lead us to calculate something called the coefficient of determination, which is more typically referred to as R squared. And then the third method that we'll tackle in another video is asking how strong is the evidence of a straight line relationship between y and x. And that will lead us to consider the slope parameter b1 and think about estimating that and testing it. So we'll talk about these second two methods in subsequent videos, but in this video we'll talk more about this first method. How close are the actual observed y values to the model-based fitted values y hat, and we'll talk about that by calculating the regression standard error S. So if we go back to the model summary, so remember we found this using R, using the summary function, and then the regression standard error S is given in this part of the output here, 2.786. I've formatted it slightly differently in this output up here, but it's right here, 2.786. And computer software calculates that for us using this formula down here. S equals the square root of the residual sum of squares divided by n minus 2. And just to remind you what the residual sum of squares was, it's the sum over the sample of the residuals squared. And remember, the residuals are the difference between observed y and fitted y. And fitted y is given by the estimated equation b0 hat plus b1 hat x. So this is the equation that the computer uses to calculate this number for us, and in this case it comes to 2.786. You might wonder why we've got n minus 2 in this formula, and just briefly, the 2 is coming from the fact that we've estimated two parameters to estimate our model. b0 hat, the estimated intercept, and b1 hat, the estimated slope, two parameters, and that's where this 2 is coming from. And then n is the sample size. So one thing to note is that the measurement unit for the regression standard error S is the same as the measurement unit for the response variable y. And that will help us understand one way of interpreting that estimate. And so we can say approximately 95% of the observed y values lie within plus or minus 2s of their fitted y hat values. And it's perhaps easier to think about that in a graph. So here's a generic picture of a scatter plot of some data, and the regression line is this solid line in the middle. And what we're saying is if we were to go to any point along the regression line, say here, and then go up 2s from that regression line, and down 2s from that regression line, and do that all the way along the line, so that would trace out these dashed lines here. What we're saying is approximately 95% of the y values, which are the points, lie within plus or minus 2s of the regression line. And this is coming from the central limit theorem, which we talked about in chapter 1. So in this case, remember this was the value of S, so this is the home prices data set that we've been looking at this lesson. S is equal to 2.786. If we multiply that by 2, we get 5.57. And remember, the unit of measurement for S is the same as the unit of measurement for Y. So this is measured in thousands of dollars. So 5.57 corresponds to $5,570. And then we use this interpretation. So we can say we can expect to predict an unobserved sale price from a particular floor size to within approximately plus or minus $5,570 at a 95% confidence level. And that's a useful thing to know about. So in this case, if a new house comes onto the market and it has a certain floor size, then we can predict the house price, the selling price for that house based on our model using our estimated regression equation, and then we can gauge the accuracy of that prediction using this interpretation here. If I take my predicted sale price and add and subtract 5,570, it's going to give me a rough prediction interval, a rough 95% prediction interval for that prediction. So that's one way of summarizing the fit of a simple linear regression model, and it focuses on how far away the points are from the regression line on average. In the next video, we'll talk about the second way of evaluating a simple linear regression model, and that's using the coefficient of determination, R squared.